Hey friends, this is Jim here with Science Talk. I want to discuss with you what we see right here. This is an article that appeared at the end of November in 2021 in the journal Nature Communications. And new climate models reveal faster and larger increases in Arctic precipitation than previously projected. Keyword projected. I'll get to that momentarily. And you can see these are the main authors: Michelle McChrystal, Julianne Streve, Mark Cereza, Bruce Forbes, and James Green. Let's look at the abstract. And I will leave the URL for those who are interested in seeing and looking at this article in more detail in the comments section below the video. And I do have some critiques of this article, although the main information presented is extremely important. As the Arctic continues to warm faster than the rest of the planet, 3, perhaps 4 times faster, evidence mounts that the region is experiencing unprecedented environmental change. The hydrological cycle is projected to intensify throughout the 21st century, with increased evaporation from expanding open water areas and more precipitation. Makes sense. You got more open water, you can pull up the moisture. Temperature is still a little cooler, so then it will, condense back down to precipitation in rain or snow form or ice. The latest projections from the 6th phase of the Coupled Model Intercomparison Project, CMIP6, point to more rapid Arctic warming and sea ice loss by the year 2100 than in previous projections, and consequently, larger and faster changes in the hydrological cycle. Arctic precipitation rainfall increases more rapidly in CMIP 6 than in CMIP 5, which is the 5th phase of the Coupled Model Intercomparison Project, due to greater global warming and poleward moisture transport, probably due to the meridional aspect of the jet stream, more meandering of the jet stream, greater Arctic amplification, right? Greater warming, greater outgassing of greenhouse gases, and greater sea ice loss, increased sensitivity of precipitation to Arctic warming. This is key. The transition from a snow to rain dominated Arctic in the summer and autumn is projected to occur at decades earlier and at lower global warming, potentially under 1.5 C, and with obviously profound climatic, ecosystem, socioeconomic impact. Let me repeat that again. The transition from a snow to rain-dominated Arctic in the summer and autumn is projected to occur decades earlier and at a lower level of global warming. Let's pause on that for a moment. Yeah, even though it's the Arctic and it's summertime, the Arctic is defined as basically, where the summertime temperature, average temperature, is pretty much 50 degrees Fahrenheit or less. In other words, 10 degrees C or less. Well, so you can still have, you wake up or, early morning, what have you. It's cool enough that you have, snow falling. Oh, it snowed here in Fairbanks in June, so it happens. But now they're saying that in the summer, so that's like June, July, August, and autumn, September, October, November. So those 6 months, you'll be seeing more rain than snow. Now, if you're seeing more rain, imagine what's happening with that rain as it lands on Greenland. I've done videos explaining that you get rain on Greenland and it just accelerates the ice loss. I did a recent 2-part video series on interactions between tipping elements. And the folks from PIK in Potsdam, Germany, concluded that a warming of 1.3 C above baseline is sufficient to throw the climate into chaos. They're hinting at that here without mentioning PIK. Now, IPCC says we're at 1.2. Bollocks, we're at 1.6, 1.65 if you look at the 1750 baseline. Once again, the little fairyland of trying to keep it under 1.5. We're already past it. And you know what? We're already seeing the climate chaos. We're seeing it all over the planet. So basically, what's going to happen here is that it's pretty much going to rain in the Arctic as opposed to snow by the end of the century. That's really the summation finding of what we're going to discuss here. Is that I'm going to kind of hit what I consider to be highlights, or what I can deem to be important to the overall message here. Those of you interested, you can click on the URL that I will provide and explore and do a deeper dive at your own leisure. There's general agreement that Arctic precipitation will increase through the 21st century, with estimates ranging from 30% to 60% by the year 2100. In other words, an increase of that amount by 2100. A wetter Arctic results from 1. Increased evaporation as a result of more open water due to sea ice loss. 2. Higher air temperatures, increasing the atmosphere's ability to carry moisture. And 3. Increased poleward moisture transport. In other words, now the poleward moisture transport can be in the form of not just what air masses are doing, like the more meridional nature of the jet stream, but also what oceanic currents will do. The oceanic currents are moving north. The moisture gets picked up off that they contain and put into the atmosphere. So again, never neglect the ocean. The Arctic is also expected to transition from a largely snow-dominated to a rain-dominated precipitation regime, a transition already being observed over the Atlantic sector, for example, in the Barents Sea region. However, uncertainty exists regarding the regional extent and seasonality of these changes. Previous studies conclude that rainfall will increase in spring, autumn, and winter, whereas rainfall and snowfall are projected to increase over some regions during autumn and winter. This increased rainfall-dominated precipitation could have pronounced and profound impact on Greenland ice sheet mass balance and global sea level, river discharge, Arctic sea ice extent and thickness, permafrost. Okay, I did a video telling you how the increased rain is helping to thaw out the permafrost in a study conducted right here in Fairbanks, Alaska, as well as flora, fauna, and linked social ecological systems. Outputs from the new coupled model into comparison project phase 6, CMIP6, experiments provide an opportunity to assess the latest projections of climate change under various emissions forcing scenarios. Relative to CMIP 5, which is phase 5, CMIP phase 6 has improved simulations of the sea ice mean, state, and trends over the period of satellite observations, as well as improved simulations of historical snow cover and global precipitation intensities. This suggests that other aspects of the hydrological cycle, such as Arctic precipitation, are also improved. So then they examine the projections of Arctic precipitation change through 2100 from the looking at the CMIP 6 and then compare that to the earlier CMIP 5 projections And the key conclusion is that the CMIP6 projects larger and faster increases in precipitation and an earlier transition to a rainfall dominated Arctic in the summer and autumn. Okay, summer and autumn versus autumn and winter, as they stated above. And so they say, so they look at the analyses and so on. And they basically state that both the CMIP 5 and 6 on average 0.04 to zero point 0.1 millimeter per day more Arctic from 70 90 degrees north precipitation over the historical time period of 79 through '05. And they go on to talk about some other, not strongly correlated to interannual variations and other issues with some of the previous studies. And now we come to figure 1. Let's go through the description here, then we'll look at a full-size image. So A is the annual precipitation means. That's this box here. Okay. Annual precipitation means over the Arctic, and they define the Arctic as from 70 degrees north to 90 degrees north latitude. And I understand that because basically, if you take it from the Arctic Circle, well, the Arctic Circle is not a fixed latitude; it changes. So, for the sake of having, definite fixed latitudes, that makes the comparisons more valid. So, I understand that, and I agree with that distinction there. B shows the annual snowfall ratio. In other words, snowfall in terms of total precipitation over the Arctic for the same observational period of 79 to '05. Basically like a 35, 36 year period. Okay, so that's the snowfall ratio. I'll enlarge this. We'll look at this in a bit. And they look at the ERA 5, the CMIP 6, and 5. The shading in both represents the 5th to 95th percentile spread in the models. Climatological precipitation for the same record over the Arctic. For C, GPCP, D is CMIP, E is ERA 5, and F is CMIP 6. The Arctic region for all time series analysis is taken as the area poleward of 70 degrees north, shown as the dark circle in C through F. So let's take a look at the full image. So here's the precipitation in millimeters per day, looking at the various models. And you can see this, the GPCP kind of takes a dip and goes back up. The CMIP, the ERA 5 is in blue. The CMIP 6 is in yellow, and the CMIP 5 is in green. What is noteworthy is that the GPCP and ERA are very jagged, kind of all over the place. Does this reflect seasonal variation? Possibly. But when you look at the two CMIPs, to me, there's less error in it. You can still see the seasonality, with less error in it. So I will take this to be a bit better reflective of the situation. And you can see the confidence interval around this basically. Both of these, both the CMIP shows, if you put a regression line through here, it shows a positive slope. So there is an increase as you go through the years of that. Let's look at B, which is the snowfall to total precipitation ratio. Again, the ERA is all over the place, to be quite honest. Really not, notice they're not even looking at the GPCP. But if you look at the two CMIPs, what do we see? Snowfall ratio is declining. And this is based on observable data already. And it's declining. Meaning that other precipitation, rainfall, perhaps ice, freezing rain, hail, that kind of stuff is increasing. That's what that means. So these look at by latitudinal consideration. This black circle is the 70 degrees latitude, and you can see right here that's right about where Utqiagvik is, formerly known as Barrow, Alaska. They changed the town name officially. It's Utqiagvik. That's right there, Point Barrow. Okay. And actually, Barrow is 72 degrees north latitude, so it's clearly within. Now let's look at the colorations here, and this is precipitation in millimeters per day. Okay? So from the darkest blue, it's 0, and we get into the green, it's 1.8, and then it gets all the way up into this light gray area of 4.8 millimeters. That's like a fifth of an inch. And what do we see? We see a lot of green outside the area of interest. When you look at the different models, right, you can see some increased precipitation. This is what they meant by the Atlantic sector, right? Is Novaya Zemlya, is the Barents Sea, right? So that's what they meant by that. When we look at the CMIP 5, all right, we see a little slight increased precipitation there. Again, it's reflected. We see most of it in the Atlantic side of things. And we see they're pretty much the same. We see a little more sensitivity with the CMIP 6 in that it does a better job of delineating how much precipitation, whether it's like 0.6 or 0.8 or so, something like that. So we can see a little better delineation with the CMIP 6 model. Annual, now taking at the whole region in consideration. Annual mean Arctic precipitation in both the fifth phase and sixth phase is consistent with ERA 5. Values around 0.94 plus or minus 0.3 millimeters per day for each data set. Further, the fifth and sixth phase multi-model ensemble means simulates similar spatial pattern of precipitation variability as ERA 5. Overall, the CMIP 5 multi-model ensemble of annual precipitation is larger by about 0.1 plus or minus 0.04 millimeters per day than the CMIP 6 over the same historical time period. We also compared the snowfall precipitation ratio, and they just say snowfall ratio. And throughout the observational period, there's a slight, statistically significant negative trend in the snowfall ratio in the ERA 5, which both CMIP 6 also reflect. And that's this right here, what I pointed out to you earlier. You look at the regression line, there's clearly a negative correlation, negative slope, meaning snowfall is decreasing. The multi-model ensemble of mean of Arctic precipitation increases in all seasons throughout the 21st century, especially in autumn. For the representative concentration pathway, 8.5. This is the worst case scenario, if you will, that IPCC uses. This total precipitation increase is largely dominated by an increase in rainfall for all seasons in both of the CMIP 6, CMIP 5 and 6. In summer and autumn, the rainfall increase is accompanied by decreased snowfall. In winter, however, snowfall continues to increase and remains the dominant precipitation type at the end of the century across most of the Arctic. Can't say that should come as a big surprise. Spring, there's little change in snowfall throughout the century. Let's enlarge this figure here, and let's take this into consideration. So this is changes in total precipitation, TP, red and orange. The snowfall is in blue, light blue. Rainfall is in green. Okay? And they're shown relative to the 1981 to 2009 climatological mean. Okay, so here's where one of my problems is. First they were looking at 79 to 05, and now they're looking at 81 to 09. Why the change? So in meteorological, you're going to have 30-year running averages. This is a 30-year running average. So if you look at period, you can look at from 91 to 2020. You can look at 71 to 2000. So you will get these 30-year running averages. That's the standard that the meteorologists and atmospheric folks do. So that could be a possible explanation for why they suddenly switched the baseline comparison. But for consistency with the other stuff they presented, like in Figure 1, it would have been preferable to stick to the same time period. Instead, they went, 79 to 2005. So little questions about that. So let's look at these here. DJF, that's December, January, February. MAM, March, April, May. June, July, August. September, October, November. Okay. And what are they looking at? Precipitation millimeters per day for the overall year. And what we see here, and we need to go all the way down, so they take it up to 2100 is the last hash mark right there, 2100. And we see what? We see, this is very important, we see an overall increase in precipitation amounts. The green is increased rain. The blue shows kind of a flat line for the snow. And this is for the period December, January, February. Now, if we look at March, April, May, we see the snow is really flatlining. And the blue is the sixth phase, that tan is the fifth phase. But once again, we see that we have increased precipitation, increased rain. June, July, August, no surprise that we see a decrease in snow, but we see more increase in the rain. And of course, precipitation total is going to be the summation of those two guys. Then September, October, November is very telling. A major drop in snow, but we see a major increase and thus overall precipitation. This, in my opinion, this Figure 2 sums up the research right here. Now, what are these things here? These are basically, I wouldn't call them cat and whisker plots, but they represent this dark blue line, the dark black line is the median. This dashed line here is the 25th percentile. This dashed line here is the 75th percentile. And so we're seeing, so that's your interquartile range. And then you're seeing, basically gives you an idea. It's like a histogram. Or a bell curve here. It's giving you the distribution of data. So you get to the minimum and maximum values. So see that here. So it's stretched out as well. But again, these are the 25th and 75th percentile. That's your median, which is the 50th percentile. So that's what these represent. They're basically, think of these as bell curves, histogram kind of representations. And it's kind of telling you the data distribution, what it is. So when you look at this here, these negative values, that is less precipitation compared to this baseline or relative to those 30 years. This is. Thus, anything in the positive is more precipitation relative to that 30 year. So that's how to view this information. And they give the breakdown for the two models here. the dashed line, the solid lines, etc. But as we can see overall, rain is increasing. And when they talk about a slight increase in snow, I don't know if you can see it, but that's this little light blue line that goes up just ever so there. And then this is the summer and autumn month, and we can see very dramatic increases in rain, and it's reflected in these bell curve histogram type graphing. And the breakdown, this is total precipitation, this is snow, this is rain. Okay? Total precipitation, snow, and rain. You can see how the snow is drastically reduced. That means that the data is really crunched together, not much happening. So as I said, to me, this sums up right here. This entire figure sums up the essence of the research, that the Arctic is going to transition to more rain than snowfall, and you're going to have significantly more rain and more, which translates to more precipitation in toto by 2100. So it's going to get wet, and it's not just snow. That's what this is showing us. So when you're watching, of course, feel free to pause the video. So I'll put it there if you want to pause and ruminate over these graphics. Anything there. So you can study it at your own leisure. And again, these are the breakdown of what the bell curves are representing. And I'll pause it there to read the description. I guess they call them violin plots. Okay, they say so. That's a new one for me, to be quite honest. All right, so moving back. Phase 6 overall projects larger increase in precipitation than Phase 5, dominated by increased rainfall. We just saw that in the diagram we just looked at, in the figure we just looked at. And then let's see, there's a 422% increase in Phase 6 rainfall compared to 260% increase in Phase 5 in winter. Corresponding values at 261, 141 in spring, 71, 51 in summer, 268, 192 in autumn. These are increased percentages in precipitation in rainfall. This results in about 0.3 millimeters per day or 27.3 millimeters per season. Difference in rainfall by 2100 between the two of CMIPs in autumn and around 0.2 millimeters per day, 18.2 per season. Difference in spring and winter. Trends are also larger in Phase 6 in autumn. Rainfall increases by 0.9 millimeters per day, 81.9 millimeters per season from 2020 to 2100, compared to 0.7 for the CMIP5. It's a pain in the ass to say this. Resulting in 24% larger rainfall increase. Larger rainfall increases are also simulated in other seasons. Winter has a 39% greater increase in the Phase 6, whereas spring and summer have 36%, 14% greater increases, respectively. There's a greater reduction of snowfall in summer, no surprise there, of 16%, and autumn, 38% at the end of the century. Autumn is surprising because autumn is when it's supposed to start cooling down. You're supposed to get more precipitation. So this is telling you what? There's more heat in the atmosphere is warmer. And why is the atmosphere warmer? Because there's more open water. The ice doesn't start forming. It's pulling that, you got the warm water diffusing in from the Atlantic and the Pacific, North Atlantic intermediate water. That heat is diffusing up into the atmosphere. That's why the air is warmer. That's why you're getting rain, not snow, because the heat is keeping the water from freezing. And it's keeping the air warmer because that heat in the water diffuses to the atmosphere. That is a very important point here, not necessarily mentioned. So they go on to postulate that the greatest spread in total precipitation, rainfall, and snowfall in the phase 6 is likely related to the greatest spread in surface air temperature, open water, and vertically integrated moisture flux, VIMF, at the end of the century. Okay, so at least they mention open water, but they don't tell you that the heat is coming from all that warm water moving into the Arctic Ocean. Accompanying this larger spread is an increase in the upper range, with the upper 95th percentile in autumn at 1.41 millimeters per day in phase 6, compared to 1.26 millimeters per day in phase 5, suggesting that greater average rainfall amounts are possible by 2100 than previously projected. And then they talk about autumn, the upper limit for the phase 6 is 1.7 millimeters per day versus 1.4 millimeters per day for phase 5. So let's quickly scoot up, and that's, and we'll look at the full size. And they're talking about what we see up here as total precipitation, snow, rainfall up here. This is December, January, February, so that's winter. March, April, May is spring. June, July, August is summer. So again, we see these upper ticks. And look at what they got here for September, October, November. That's your autumn. And talk about 1.74. That's this right here for the rain. And then for overall total production, about 1.4 or so. And remember, the blue is phase 6. The tan, brown, whatever, is phase 5. So you can get an idea of the spread and how much more precipitation compared relative to that 30-year baseline will be. And again, we see that reflected in the projected pathways. Look at figure 3, snowfall and rainfall changes in the phase 6 and the difference between the phase 6 and phase 5 snowfall and rainfall at the end of the century. Now this is a graphic I thought it was just a little bit on the confusing side, a bit too busy here, and it just wasn't quite clear what they were trying to represent here. So let's take a look at this. Okay, so looking at December, January, February. So this row is snow, this row is rain. And September, October, November. Okay. Why put December, January, February first, then September, October, November? I think they should have taken these 4 on it first. This should have been first and then the December, January. That's just so you see the continuity. So I had an issue with that. Okay. The left-hand column shows the changes in A and E snowfall. Okay. So you have to jump up here, A, the snowfall in December, January, February, jump down to E, the snowfall September, October, November. Okay, so you have to do that. And CG, rainfall. Okay, there's G, the rainfall in autumn, and C is the rainfall in the winter. So you have to kind of bounce back and forth here. It's not nicely, conveniently placed next to each other for, in my view, easier comparisons. And then, so this is at the end of the century. In A and C, this is the winter month. E and G are the autumn months. So this left-hand column, all these figures in left-hand column are the phase 6 results. Then the right-hand column shows the difference in B and F, the snowfall. B and F, there's B, there's F, that's the difference in snowfall. And then D and H, the rainfall at the end of the century, the last decade or so. D and H, so there's H, the rain, and then D up there. So D would be, and in the winter months, H, difference in rain for the autumn months. The hatching indicates statistical significance at the 95% level. So in other words, they're showing the differences in the precipitation amount for rain and snow for the winter and autumn months, and the difference is in the right-hand column, the difference between the phase 6 and the phase 5. And what they do is it's phase 6 minus phase 5 because phase 6 was showing higher values. So what they're basically saying is that all this hatching, the phase 6 model is significantly different from the phase 5 model, indicating that the phase 6 is probably showing greater changes. In other words, the phase 5 model underestimated, phase 6 has been an improvement, and the improvement has been such that the results of the models are such that phase 6 is significantly better than phase 5. That's kind of what they're trying to indicate here. It said to me is this: you have to bounce around too many times here. So this is significant, right? That's the difference in snow. So you're getting more snow basically in the Barrens. You're getting more snow over the Canadian archipelago. What are these scales here? Okay. The precipitation in millimeters per day. So when you get to the brown, that means what? That's in the case for the snow, there's less snow. In the case for here, the light blue indicates that you're probably going to get a little bit more snow. That's what this is telling us. But look at this, at the models here. Look at how much less snow this is going to yield. How much less snow you're going to get. That's what this is telling us. Okay? This is minus. So you're going to get far less snow. And then when you look at and look at the flip-flop here. Okay, see the dark brown here? That's less snow, indicated here. But now look at this deep blue, there and there. And that's for the rain. That's considerably more rain. So this is showing us, right, this is for the winter months. This is showing us that the snow changes to rain. That's what this is telling us for the winter months. And this is telling us, where the phase 6 model is significantly different from the phase 5 model. I mean, you can just compare them. Look, phase 5 definitely underestimated. So again, let me stress this once more. Less snow because it became more rain. Now looking at the autumn, and we're seeing less snow, flipping to become more rain at 2100. That's what this is showing you. That's exactly what this graphic is meant to indicate. Again, couple seconds there. Couple seconds there. Likewise. Likewise. Those of you who may want to pause the video and study these graphics. And then there's the description. So you can see they're definitely making, they're making a very strong case that, taking into account everything that's happening, all the Arctic amplification, the warming, the exponentiation, the fact that the Arctic is warming now maybe perhaps 4 times faster rest of the planet, taking into account less sea ice, more open water, moisture levels increasing, that there's going to be a changeover, that the Arctic will become more rain precipitation driven versus snow precipitation driven. In other words, the Arctic will be raining a hell of a lot more often than it's snowing. And that is extremely concerning. So now they go on to discuss the drivers of the precipitation change. Stronger Arctic precipitation increases in the phase 6 model could be the result of either a greater sensitivity of precipitation change per degree of warming, defined here as percent of change in precipitation per degree of Arctic or global warming, or more pronounced warming in the phase 6 models, or both. During autumn and early winter, phase 6 exhibits a stronger precipitation increase per degree of Arctic global warming than in phase 5. That's what the right-hand column is showing with all the hatchings. Although the difference between this phase 5 and 6 is smaller for the sensitivity to Arctic warming. The relatively larger difference in precipitation sensitivity to global warming than Arctic warming in phase 6 compared to phase 5 reflects the larger Arctic amplification of warming in phase 6. Slightly larger precipitation sensitivity to warming during the freeze-up season may in part explain the greater change in projected autumn precipitation. Translation: what I said earlier, the water staying open longer, you have heat diffusing to the atmosphere, it's warmer, so it's going to come down as rain. The ice is not freezing, so you're not going to get the precipitation in the form of snow. So, in figure 4, they look at the sensitivity of precipitation to temperature change throughout the 21st century. Let me enlarge this again. And so we see the sensitivity. It's on a scale of 0, I'm assuming, compared to the 81 to 09 reference period. So you could have a decrease possibility, decreased sensitivity, where you can see the sensitivity goes up to 17.5. Okay. The percentage change of total precipitation per degree of Arctic warming, global warming by month. So per degree of Arctic warming, and then compared to the planet warming by month. Okay. So this is, sensitivity is really a percent change. The black dashed lines represent 25th, 75th percentile. Black solid lines represent the, I was saying model mean, okay, as opposed to median. And again, they're looking at, for example, the SSP to 8.5 to the RCP 8.5. And of course, the RCP is that what? The IPCC likes to use that a lot. What's that? The representative concentration pathway. And as you can see, starting in May, we're running through September into October. So this 6-month period, we see a large sensitivity. In other words, a large increase in the change of precipitation as a function, basically, of how much warming in the Arctic, and then for the planet. And as you can see, for the planet, it's has a much wider range, although in July, in both of them, we see some low values showing a percent change decrease. Probably some outlier, a couple more in August and September. Possible outliers. Once again, the blue is phase 6, the brown, tan, whatever, is phase 5. So 75th percentile, 25th, they're saying that's the mean. I thought it was the median. There is a difference there. And then these are probably your lowest value and then your highest value. But we see very sensitive and it's going to respond accordingly to how much warming. And I don't know if I can get, I guess I can get both of these just like that. You guys know that the blue is phase 6 and the brown is phase 5. So there. So again, if you wanted to pause and look at this, you can. Okay, back. In both CMIP ensemble, the magnitude of rainfall increase and snowfall decrease at the end of the century is statistically significant, correlated 95% level with R values between 0.6 and 0.89. Now, R values is correlation values. In other words, is there a relationship? This is not R square values, which tells us how well the data fits the regression model. Right? What this is telling us is that we have good, strong correlation with the magnitude of Arctic warming in all seasons. It's large, with the maximum value from one phase 6 model projecting up to 23 degrees C warming at the end of the century, compared to 18 in the phase 5. Okay, well, those might be, you do some tests there, those could be outliers, but 5 to 11C, as I keep mentioning, by the end of 2100, it's not unreasonable, looking at that here, to see such a spread. Of course, that's based on precipitation change, but of course, warmer air can hold more moisture. So it's probably that range there up to the 23C or the 18C. That is most likely to be reflective of how much warming can be in place by 2100. Is it at the 5C level or is it up on the 11C end of things? And that, of course, for every degree C, the air is warmer, you can hold approximately 7% more moisture. That even with the, looking to say if you have moderate temperature increases, the phase 6 does show a greater magnitude of rainfall increases across the models with the amount of Arctic warming. We hence partly attribute the differences in precipitation projections in phase 5 and 6 to stronger projected increases in global and Arctic air temperatures in phase 6. However, larger magnitude global warming is insufficient to explain the faster projected precipitation changes in phase 6, especially in autumn. As we find that for the specific levels of global warming, 1.52 and 3C above pre-industrialization, underestimation, folks, there is more rainfall at all warming levels because what I just said, for every degree increase, every degree C increase in air temp, you can hold about 7% more moisture. Thus, the faster the rate of global warming, the greater magnitude of Arctic amplification, the greater sensitivity of precipitation to warming likely all contribute to the more pronounced precipitation changes in phase 6 compared to phase 5. In other words, it's just going to precipitate a hell of a lot more as the warmer the planet gets. Okay, so let's take a look at this here. Let me enlarge. And by the way, I don't know if I mentioned it, but SSP is shared the socioeconomic pathways. And basically it's, taking into account any mitigation efforts that humanity employs or not. It's a major problem that I have with the IPCC reports because a lot of their models, especially when you look at the RCP, they have all these different projections, and they're they put into the model assumption that mitigation will actually take place when we're not really seeing evidence that they are. So that's why when I look at models, okay, yeah, they got the CMIP, right? The intercomparison that we've been discussing. I like the models that the PIK folks in Potsdam, Germany, have developed, and they've been developing, and they keep refining it, and as more data comes available, we understand the interactions better, so we improve the equations, etc., etc. And they allow for exponentiation. That's in the models. Only the RCP was at 8.5 actually kind of allows themselves the worst case scenario, which is now what more and more studies are utilizing. But the program that the PIK folks use is called, the acronym is CLIMBER. I forget what the acronym stands for, but it's independent and separate from RCP, CMIP, etc. So I just wanted to put that out there. Now here's an example where everything is just so bloody busy. So we got the blue dot is the phase 6 snow, a pale X. Blue X is phase 5 snow. The red dot is phase 6 rain. The pale or light red X is phase 5 rain. Okay. So again, they break it down by seasons, right? December, January, February, March, April, May, June, July, August, September, October, November. And again, they do the precipitation, millimeters per day. And then they look at temperature, open water, and how many millions of square kilometers, and then the vertical integrated moisture flux. In other words, kilograms per square kilometer. And now they go per second squared. So this is an acceleration. That's what's the velocity per second? That's acceleration. So kilograms per square meter per second per second. So intermodal dependence of snowfall and rainfall to ADGI, which is the vertical column, the first vertical column. Surface air temperature, the middle vertical column. Open water, and then the vertically integrated moisture flux, the third column. So they're looking at the model of snowfall and rainfall to the surface air temperature, open water, and the VIMF. And looking at the end of the century relative to the start of the century for, and I broke down the seasons for you. Each dot represents a model from phase 6. Each X represents a model from phase 5. The stars represent the multi-model means for either phase 6 or 5, snowfall to rainfall, in the same colors as their representative individual members. The line of best fit is calculating using a 1D polynomial. 1D. Is that linear? Don't assume linear. So when you look at this here, okay, for precipitation, basically shows an increase in rain, probably no change in snow. That's based compared to temperatures. March, April, May, snow looks like it's slightly decreasing, probably maybe not significantly different from zero. We see more increase in rain, right? Wrong way. Okay, then June, July, August, the snow is definitely decreasing. Rain is increasing. And then in autumn, this is where we see major increase in the rain, and we see a decrease in snow as a function of temperature. Now for function of open water. More rain. More rain. More rain, less snow. A lot more rain. You can see the improvement of phase 6 over phase 5. Open water. Heat flux. Air is warmer. All right, precipitation will come down as rain. And then when you look at the moisture flux, that to me is indicating the flux from the ocean to the atmosphere. And this is very telling. We see rain still increasing in December, January, February. That could be reflective of that not all the ice had formed yet, hadn't totally frozen over. March, April, May. This to me is an interesting result because March is typically the oceanic winter. I would have expected this to be at least flatlined. So this to me is a surprising result. Then you get into summer. This makes sense, right? You have increased flux rate because you got open water, less snow, and then this reflects once again how the heat diffusing is keeping the water from freezing. As we can see here, the autumn is where things are getting crazy. And I can tell you from what I've been observing quite a few years here in Alaska is that October has been the month that we've seen the greatest deviation in air temperature from historical records. October has been considerably warmer. It's the month of the year here in Alaska that has warmed the greatest when you compare it to historical records. And that's because the heat is keeping the Arctic Ocean open, so we get that flux, the diffusion of the warm air, and we see that. And it's also why we talk about this increased rain. That increased rain is coming down and freezing. And I'll tell you, it's a bitch to drive on basically ice. I mean, it's becoming. I mean, I would probably get to my destination faster if I just simply strapped on my ice skates. Seriously. And so we're seeing that here, and this is being reflective. So this is further evidence for the case that they're making, and I think they are making a good case here, of that there's a transition underway that snowfall may become almost a relic in the Arctic by the end of this century. End of century changes in sea ice concentration, temperature, and the vertically integrated moisture flux. Okay. And the century changes in sea ice concentration or open water areas. And actually, this is what they should have been doing all along here. Here's your seasons. Bam, right there. In order. Yeah. So let's take a look at this enlarged. The end of the century changes relative to the start of the century in all seasons in A, open water area, million square kilometers, B, temperatures, and C, the vertical integrated moisture flux. Again, blue is the phase 6, and they're calling that orange. Okay, well, that doesn't look orange to me, where the colors represent the kernel distribution. And again, the same thing as before. Mean, 75th, 25th percentile, max, min, values, etc. Changes relative. In other words, there's more open water. This is not actual open water. There's more open water by this amount at the end of in that 10 years versus this 10 years. That's what this is saying. So this tells us there's going to be more open water in the winter months at the end of the century than in that 05 to 2014 time frame. In other words, we're losing the sea ice. Why is it the fewest changes in June, July, August? Because that's when you're going to have you have a lot of the sea ice that's already melted. So this is going to reflect, this does not come as a surprise. This is an expected result that there's less ice loss because it's already pretty much summertime. But we could be seeing the blue ocean events here. So these results here during the winter into the springtime, although remember, March is the oceanic winter. This is telling us that this, compared to 05 to 2014, there's going to be a hell of a lot less sea ice. And compared to, again, those years there, it's going to be a hell of a lot warmer. Summertime is not going to be that much warmer because this is already the warmest time of the year. So these are pretty much reasonable results and projections. Then the flux, however, is really interesting because, and this again is not a surprising result, you're just going to have, you're going to have a lot more open water, you're going to have a lot more flux of moisture and temperature and so on from the ocean to the atmosphere. That's what this is showing. Okay. Okay, let's see. Look at this one here. Arctic rainfall changes per season relative to global warming scenarios. So now they break it down to 1.5 C world, 2 C world, and 3 C world. And they look at rainfall change in millimeters per day for the three scenarios. And then they break it down by season. And I'm assuming it's going to be relative to that 05 to 2014 time period. And in a 1 point, so let's see. So that's winter, spring, summer, autumn. Okay, so we start with winter. And well, that's a little interesting blip there. But basically, 1.5 C, going to be some changes, not much for winter and spring. We see great changes in the summertime, considerably, and the greatest changes in the summertime. Second greatest is in autumn. Notice for the 2 degrees C world, it's about the same for winter. It's a little fatter. It's a little bit more in the springtime. About the same for the summer, about the same for the autumn. Now look what happens in the 3C world. We see an increase in all seasons, relatively speaking. So that's what that's showing. Then to go on to do a little quick discussion and say, not surprising, sea ice area declines faster in phase 6 than phase 5, leading to larger areas of open water. At the end of the century, relative to the start, phase 6 projects nearly twice as much open water in winter compared to phase 5, resulting in a larger Arctic moisture source. And therein is, and this is what I've been saying, open water, more moisture in the air because of the heat diffusion, etc. This is what I've been saying all along. So, as the temperature increased, the magnitude of the increase in open water area at the end of the century across the models is significantly correlated. R values between 0.53 and 0.92 with the magnitude of the increase in rainfall in all seasons, with the magnitude of snowfall decrease in summer and autumn, around minus 0.99 and minus 0.76 respectively. The values for R range between -1 and +1. That's almost like perfect negative correlation. Very rarely see that. Okay, transition to a rain-dominated precipitation. As a result of the above-mentioned differences, the transition from snow to rain-dominated precipitation regime occurs earlier in phase 6, particularly in autumn, with most of the Arctic Ocean, Siberia, and the Canadian archipelago becoming rainfall-dominated 1 or 2 decades earlier. Phase 6 shows a more rapid reduction of the snowfall ratio from around zero point 0.7 at the start of the century to around 0.3 at the end of the century. Figure 9D. Have we looked at 9D? 9D is down below. So let's take a look. Let's zoom down to 9D. 9D. There we go. Whammo. We'll take a look at this in a moment. Indicating a more rapid loss of snowfall in phase 6. By contrast, despite large reduction in snowfall or precipitation ratio, most of the Arctic remains largely snow-dominated winter-spring throughout the century. Regionally, however, a transition to rainfall regime in both winter and spring occurs in about 10 years early in the Barrens, because it's pretty much open year-round now, but transitions later in phase 5 in parts of North America and Europe in spring. This later transition spring is likely due to the higher snowfall ratio in phase 6 at the start of the century, although the snowfall ratio remains above 0.5 in winter throughout the century. The winter snowfall ratio, similar to autumn, still declines more rapidly in phase 6 than phase 5 at around 0.85 for both of them. Summer, the Arctic is largely rainfall dominating in both the models, except for north of 80 degrees. So here's the decade of transition from snow to rainfall. So these different colors are the different decades, and then the decade difference. So the decade of transition from snow-dominated precipitation regime to rain-dominated regime. First column is phase 6, middle column is phase 5, and then the difference in phase in the third column. Taken as when the annual snowfall relative to annual precipitation goes below 50%. Areas that do not transition by 2100 are shaded in blue. Areas shaded in white in the first two columns are rain dominated before the year 2000. So basically, what's the blue indicate? More than 21, greater than the year 2100. So December, January, February, should not be surprised that you'll still get at least some snow. Okay, not much of a difference there. And then we see the creeping starting in the spring. See it creeping in, right? So this, what color is that? Gray? That color. It's about 2030. Interesting. Creeping in. This is 2040. But now look what happens when we get into June, July, August, okay? Yeah, that, not a surprise. It's summertime, so you're going to get rain. And then look at the autumn. This is where we see the greatest change. Now we got, what is it? Looks like a pale green, a light green, and a darker green. So we're starting in 2060, 2070, 2080. This is where we're seeing the most dramatic changes. And we can see that this phase 6 does a better job than the phase 5. And then this is your decade difference. So in other words, phase 6 is telling us 1 to 2 to 3 decade difference. And again, this is reflecting that the Barrens is pretty much open water year round. So what we're basically seeing from all this is that the critical season is autumn. That's the critical season. And I kind of briefly described a few moments earlier why that is, or possible reasons for why that is. Okay, let's look at figure 9. Time evolution of the snowfall ratio. So winter, spring, summer, autumn. And by 20-year increments. And the snowfall ratio goes from 0 to 1. And the blue is phase 6, and I'm still calling it tan, is phase 5, with again the confidence intervals around it. In all the seasons, we see a decrease. In all the seasons. Even in the summertime, there's still a decrease. But look at the autumn. This is the most dramatic decrease. It's going from basically 0.72 or so down to 0.3. Major reduction in the ratio. That is, the autumn has the greatest reduction in the ratio. In other words, you're losing a shitload of snow. And by the time the century ends, the snowfall is vastly, greatly reduced. And they put in this horizontal line showing the transition from snow dominated to rain dominated. So, not surprisingly, this is, if it's under the line, it's rain dominated. Above the line is snow dominated. So, wintertime, snow dominated. Makes sense. Springtime, winter's still lingering, gets a little closer to changing. Summertime, it's rain, so of course it's going to be rain dominated. But here's, again, the autumn. It changes from snow to rain dominated. And if you look at phase 6 model, that's taking place around 2065, 2070, according to them. I'll repeat again. They are demonstrating that autumn is the critical season. So now they get into a little discussion here as to different types of scenarios. Projected precipitation change under global warming scenario, given the argued necessity to stay within 1.5 to 2 degrees global warming. Ha ha, good luck. To mitigate against severe climate change, we're already at 1.665 if you look at the 1750 baseline. Let's explore how these temperature limits relate to the transition to rainfall-dominated precipitation. Assessing across different regions annually, Beaufort, Chukchi, Bering, Laptev, and East Siberian seas remain snowfall-dominated in both the 1.5 and the 2C warmed world, whereas transition to rainfall will occur likely in the Greenland and Norwegian seas, regardless of 1.5 or 2C limit. North Atlantic intermediate water bringing in warmer waters. The Barents Sea is basically ice-free now. We have Atlantification of the Eurasian, especially the Eurasian side of the Arctic Ocean, as I discussed in a recent video. The Atlantification of the Barents and Kara Seas. Check out that 2-part video. In Western Russia and Europe, the transition rainfall is more likely to require 2-degree global warming, with more phase 6 models showing the shift than phase 5. Greenland is expected to transition to rainfall-dominated precipitation with 1.5 degrees C warming in phase 6 only, but in both models when 2 degrees warming takes place. We also analyzed the snowfall ratio for 3 degrees of global warming, as the likelihood of staying under 2C warmings is believed to be only around 5% given current policies. Well, that's not too confident now, is it? And quite honestly, that's realistic. At 3 degrees warming, most regions, except those on the Pacific side of the Arctic, have already transitioned to rainfall-dominated regime. However, seasonally, as indicated in Figure 10, winter remains snowfall dominated by the end of the century, and at 3 degrees global warming, most regions remain snow dominated in winter and spring. But if the warming is 5 to 11, then I'm going to tell you right now it's going to be rain dominated. So let's take a look at this figure here. And again, it's kind of like all over the bloody place here, but here's the snowfall ratio. 1 5 degree world, and let's see, and so they're looking at they break it down by the different locations. So you got Siberia, West Russia, Europe, Greenland, North America. Well, that's kind of big. Greenland, Norway Seas, the Barents Kara Seas, Laptev East Siberian, Chukchi Bering, Beaufort, and then Central Arctic. And again, the horizontal line, the solid blue line, identifies the snowfall ratio is at 0.5. In other words, above the line, snow dominated, below the line, rain dominated. And when you get to 3C, except for Siberia, Siberia is kind of transitioning or wants to, about 50-50, but West Russia, Europe, Greenland, North America, Greenland, Norway Seas, the Barents Kara Seas are going to be rain dominated. Laptev, East Siberian, Chukchi Bering, Beaufort, Central Arctic will still be snow dominated. And you can draw the similar determinations from looking at the 2C and 1 5C world. That's what this is showing. Again, to me, the warming is going to be much more than 3C. If the planetary is from 5 to 11C, it's going to be much higher for the Arctic, in which case, I will tell you, I would go out on a limb and basically say that all of these will be rain dominated. Our analysis points to larger increases in Arctic precipitation in phase projections, with the shift to an annually rain-dominated precipitation regime occurring approximately 1 or 2 decades earlier, with the greatest changes expected in autumn, what I've been driving home throughout this discussion. The earlier shift towards rain-dominated regime has implications for the stability of social ecological systems in the Arctic and the rate at which system changes will occur. This includes a further reduction of snow cover duration, which influences seasonality, ecosystem processes such as tundra greening, wildlife populations, and human livelihoods. For example, the natives that go hunting for seals, they kind of need sea ice, right? Reduced snow cover will further exacerbate Arctic and global warming through albedo feedbacks. In other words, albedo is reduced, so more heat energy is absorbed, and warming oceans will bring extra heat into the Arctic Ocean. Increased winter CO2 fluxes, methane releases from soil, and thawing permafrost. These will additionally affect soil moisture, groundwater, influencing flood risk. The transition to more rainfall will also impact the frequency of rain on snow events, which can be devastating to wild caribou, reindeer, and musk oxen. What they're basically getting at is that you get the rain and it'll freeze on contact with the ground, so it coats the lichen, and the caribou rely on the lichen. If it's just snow, the caribou can, using their hooves, just move the snow away and eat the lichen. They require that lichen to live. Well, now if the lichen is ice covered, it's going to be deleterious for the caribou and the other. Reindeer is basically caribou. It's like tamed caribou. Massive mortality following major ROS events has important social, ecological, cultural, and economic implications. Because if you're, say you're in northern Finland and you're using reindeer, you rely on the reindeer for transportation, food, fur, etc. If they start dying, well, that doesn't bode well for humans. Increased precipitation may lead to increased river discharge, hastening sea ice loss, and freshening of the ocean surface. However, stream flow reductions have also been found following a transition to rainfall-dominated precipitation regime due to greater evaporation from atmospheric warming. And I will also postulate that as the ground starts to thaw out, you might have more percolation increase percolation rates of the water into the ground so that less will flow into the ocean surface. Changes in precipitation over sea ice areas will alter the thermodynamic ice growth and snow depth, hence the amount of light reaching the underside of the ice. Now, this is very important. Okay, on the underside of the ice, if there's no snow cover, you can find sea ice algae. Very important for productivity. I did a video on sea ice algae. Now, if it's covered in snow, okay, so the snow increases albedo. You're not going to get the sun energy to the underside of the ice. No snow cover, albedo is slightly reduced, but you're going to have sun energy getting through the ice, and then you can have the algae doing their thing, photosynthesizing, etc. And right here, changes in light transmission, altering phytoplankton algal bloom, will have cascading impacts throughout the marine food web. The projected increased snowfall over Greenland in Phase 6 may mitigate mass loss from increased melting, potentially stabilizing the central part of the ice sheet. However, Phase 6 also projects greater rainfall around the southern and coastal edges of the ice sheet, which may destabilize these regions and accelerate Greenland's contribution to sea level rise. Greenland melt has already been shown to be at least twice the rate in Phase 6 than Phase 5 under the same radiative forcing. In other words, basically saying, we're not sure where this is going to happen, but we are seeing increased rain over Greenland. I've discussed that. And rain will melt rain is warmer than 0°C, right? And so it's going to melt the ice and it's going to increase the melt. And then they get into how they go through the whole methods, etc. I'm not going to discuss that. So to sum this all up and pull this all together, what they're showing is increased precipitation amounts overall. And we're going to have increased precipitation amount because of more moisture in the atmosphere brought forth by having open waters, jet stream bringing moisture that way, greater oceanic heat diffusing that more heat to the atmosphere. For every degree C increase, a 7% increase in moisture content. So you're going to, overall, there's going to be more precipitation. What they're saying is, as the warming continues and all these factors continue, that you're going to see within this century, by the end of this century, that the Arctic in certain regions will become rain-dominated versus snow-dominated. And if the warming, and I'm projecting, because they're only going up to 3°C, but if you go up to 4, 5, 6, 7°C, then I am saying right now that you're going to see a rain-dominated Arctic, not snow-dominated, for all regions of the Arctic. Right now, they're showing, what are they showing here? Let's look at that figure. Yeah, they're showing what? The Barents and Kara Sea and the Green Norway Seas. Okay, that's the influence of North Atlantic Intermediate water. This is the Barents Sea is basically open nowadays. You're going to have a lot of heat flux there. So yeah, it's rain dominated. And oh, by the way, Greenland's not too far away. So and the season with the greatest, that's going to show the greatest change is autumn. So it's going to be more precipitation. Autumn shows the greatest changes, probably when you get the more rain event. And depending on how much warming, depending where in the Arctic, you're going to see a possible transition, a likely transition to rain-dominated versus snow-dominated precipitation regime. That's what this is all indicating, and this is all a result of what humans are doing to the planet. So, I had little issues how they presented some of the data, but overall, very good research. You can make the arguments you want about using RCP, CMIP model, be that as it may, whether, 1, 2, 3°C warming, be that as it may. Okay. What they're showing is very telling. And I would really like to see them run these models again, showing 4, 5, 6°C warming and see what the models indicate. I would really like for them to do that. So, I think this is an important piece of research, and I wanted to share this with you. So, Thank you for your time, and until next time, we'll talk soon. Hello folks, this is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.